NASA is constantly exploring new frontiers by using science and technology to improve our way of life here on Earth. For the past century, the global demand for energy has increased steadily as a result of tremendous population growth and the continuing demands of the electronic economy. However, traditional energy sources such as coal, oil, natural gas, nuclear power, and others are either finite in their availability or can contribute to negative effects on our environment. In its search for long-term solutions to the need for affordable and abundant energy in space, as well as on Earth, since 1995, NASA has conducted a series of studies and research to pursue the possible feasibility of space solar power, also known as SSP, as a viable energy source. The conclusion from these efforts to date is that while the technical challenges continue to be daunting, SSP has the potential to help meet our energy needs in space and here on Earth, and therefore merits further research and investigation. The concept of space solar power would require large satellites to be placed in what is called a geostationary orbit, high above the Earth. Once there, where the sun shines almost continuously, these satellites would collect that solar power and transform it. The energy would then be beamed, for example in the form of radio waves, down to large receivers on the Earth. The idea of producing electrical power from the sun is not new, of course. Sunlight has powered hundreds of satellites launched during the more than 40 years since the beginning of the space age. The major difference is that space solar power systems would capture large amounts of solar energy and beam it wherever it was needed, including down to the Earth for our use. NASA has also made great strides in developing some of the technologies necessary to make very large SSP systems a reality in the next 20 to 30 years. This program will allow you to see some of the advances that NASA and a strong team of participating companies, universities, and others have made in recent years. The program will also explain how some of these new technologies go far beyond their use in someday sending solar energy from space down to the Earth. But first, I'd like to introduce you to the man who invented the concept of the solar power satellite more than 30 years ago, Dr. Peter Glaser.
Thank you for the opportunity to discuss a subject that has been very close to my heart for 30 years, and that is space solar power, which can meet this century all the requirements for energy on this planet. The way it got started is the realization that we are running out of the availability of fossil fuels. We now know that reliance on fossil fuels is going to create unacceptable global warming. We also know that we have the capacity to go this route and have it ready by the middle of this century to meet most of the energy needs on this planet. Since 1963, I have participated in the U.S. space program, and thus to be able to come up with the concept of solar power satellites, as it was first called, was rather easy for me, because I believe that we have the capacity in the space program to do all the developments that are necessary to demonstrate that we can convert solar energy in space for use on Earth, and do so within the next 10 years, and then go on to do this on a global scale. The support of the U.S. Congress and NASA was, of course, essential to achieve this, and I'm delighted today that many different countries believe that this is the way to go. It is no longer whether we can build solar power satellite, but how best to build them. And I hope that I will be able to be still of some assistance as this project goes forth, and that we will solve not just the technical, but also the economic and societal and, if you like, political problems that this will entail. So good luck, And let's hope we can achieve it in this century.
Significant demonstrations and verifications of electric power transfer efficiency and high power delivery at long range have been accomplished by NASA.
An alternative to photovoltaic technology is to pump a suitable high-power laser by using the sun's radiant energy directly.
Quantum dots have the potential to provide lightweight, low-cost, high-efficiency solar cells.
The Rainbow photovoltaic array concept offers the combination of high solar energy concentration and high-efficiency power output.
This concentrator collects light from a larger thin-film inflatable primary concentrator and focuses that energy into a high-temperature receiver. Solar arrays that do not arc at voltages up to 1,000 volts have then and are being designed and tested in a simulated space environment. While the array regulator offers the potential to regulate extremely large loads of power for SSP, it also provides benefits for future NASA missions.
At NASA, researchers are developing new concepts for lightweight structural elements such as inflatable trusses. Because it uses less material, an isogrid boom is lighter than a simple tube, but it has almost the same strength since the fibers are placed only where they are needed to carry the load.
Thin-film solar cells offer tremendous promise for space solar power by creating more efficient, lightweight, and cost-effective solar cells.
Highly advanced space transportation vehicles launched from high-throughput spaceports will allow very low-cost delivery of the materials and components needed to provide energy from space.
While the Hall thruster is very fuel efficient at kilowatt power levels, the MPD thruster provides better thrust density and performance at megawatt power levels.
New generations of robots, such as Johnson Space Center's Robo-Naut with its ability to handle extremely intricate and precise tasks, pave the way to the future of robotics.
Each of the two solar array panels is 10 square kilometers. Each row in the panel is individually driven to continuously face the sun.
One candidate architecture for SSP power generation and transmission is the Halo concept.
The use of high-power, high-temperature electronics offers potential benefits for both microwave and laser-based power transmission systems by reducing the mass of the wires and the size of the thermal radiator.
A robotic mission to the moon can mature space solar power technology and answer key scientific questions.
NASA is currently investigating two fundamentally different approaches to achieve wireless power transmission by which the sun's energy might be moved in space and delivered from space to markets on the Earth. One likely method is to convert the sunlight into a low-intensity microwave beam, as discussed in another video segment. The other is through the use of electric or solar-pumped lasers. While a microwave beam is the most efficient approach, it requires a very large transmitter, called a phased array, to operate successfully. Alternatively, even though less efficient, a laser-based approach might start smaller, using multiple satellites that could be launched individually, unlike the single, very large platform needed for microwave power beaming. Next, you'll see some of the advances that NASA and its team have made in the concepts and technologies for both microwave beaming and laser power beaming for wireless power transmission.
The technology of wireless power transmission is not without precedent. Significant demonstrations and verifications of electric power transfer efficiency and high power delivery at long range have been accomplished by NASA. The most dramatic of these was the NASA JPL Goldstone demonstration conducted in 1975, in which 34,000 watts of power was safely transmitted over 1.5 kilometers at an efficiency of greater than 82%. It was then, and remains today, what can be called the world record for high-power, long-distance wireless power transmission. The NASA JPL Venus Station 26-meter antenna, with its 500,000-watt transmitter, was used to perform a 1.54-kilometer wireless power transmission to a rectenna array located on the Goldstone site's collimation tower. 4,590 rectenna elements with high-efficiency gallium arsenide diodes were fabricated at the Raytheon Microwave and Power Tube Lab and assembled in rectenna subarrays of about 1 meter square. From each DC output of the 17 subarrays, approximately one-third of the power was routed to a pair of 300-watt lamps. The lamps were arranged in the geometry of the rectenna array and wired to corresponding positions such that illumination of the lights would represent the received power beam at the rectenna. Of the calibrated RF power flux density that fell on the 24-square-meter rectenna array on June 5, 1975, 82.5% was collected and converted to direct current output.
It can be seen from the results of the successful 54% end-to-end laboratory demonstration of wireless power transmission and the successful test at Goldstone of sending 34 kilowatts at a mile range that we can confidently predict the performance of a wireless power transmission system, whether it be direct or laser or microwave or with relays, and this technology should help NASA have successful missions in the future.
An alternative to photovoltaic technology is to pump a suitable high-power laser by using the sun's radiant energy directly. Here we see one possible application that would allow spacecraft and satellites to be powered from a remote energy station. Spacecraft that are designed to utilize this resource would not have to carry their own solar panels or radioisotope thermoelectric generators, and would therefore only require a small battery to supplement power delivery during periods when the beam is not available. Currently, spacecraft designs and operations are limited by the availability of energy resources. Technology such as this would pave the way for expanded space missions. The ultimate application is powering human activities on Earth. Here we see a number of directly pumped solar lasers that are orbiting the Earth high in a geosynchronous orbit. Even though there appear to be several independent satellites in this constellation, they work together to form one local satellite system. There would be many such satellite systems in geosynchronous orbit. Ultimately, the energy beams from these satellites may either be concentrated at one receiving station on Earth or sent to many smaller and remote receiving stations where the energy is most needed. The directly pumped solar space power satellite is a technology under development that has great potential to solve many of the current limitations in power beaming technology and light the way to a brighter future for humanity.
The continuing role of systems integration within the Space Solar Power Program has been to contribute to the development of new satellite and system architecture concepts through an analytical process that is used to assess the value and requirements of new and advanced technologies that might be used in these systems. The process also examines the satellite concepts themselves in terms of the estimated mass, cost, and the ultimate price the public would have to pay for electricity delivered by these satellites. In our efforts to find ways that would reduce the projected cost of electricity produced by SSP, many different solar power satellite concepts have been proposed. They run the gamut from smaller 50 to 100 kilowatt systems based in low Earth orbit to huge multi-gigawatt systems in geosynchronous orbit, the same orbit populated by most of our communication satellites. Some transmit their power via microwave energy similar to what is produced in your microwave ovens at home. Others would use laser energy to transmit their power to the ground. One of the earliest concepts proposed and examined over the past several years is the sun tower, a long, tower-like configuration with circular, concentrated solar collectors running along its length like petals on a long-stem flower. At the bottom of the sun tower is a large microwave transmitter that always faces the Earth as the satellite traverses its orbit. The design is simple and relatively easy to assemble in orbit. However, due to the sun tower's orientation in its orbit, each day the solar arrays would go from full solar illumination to full or partial shadowing, caused either by the Earth or by the arrays themselves. Also, its unique configuration requires that the sun tower grow to many tens of kilometers in length in order to deliver the desired power levels to Earth. This means that the electrical cables bringing power from the solar arrays to the transmitter would become extremely long and heavy. The way for a solar power satellite to avoid the varying illumination problem is to employ an orbital configuration that allows the satellite to maintain its solar arrays pointed at the sun while letting its transmitter slowly rotate so that it is always facing the Earth. This was the design approach taken by the early solar power satellite study performed in the 1970s. More recent concepts developed during the course of our current studies use a large rotating reflector to redirect the microwave energy to Earth. This latter concept has been named the abacus reflector due to the appearance of its two-dimensional array structure. While the added array dimension reduces the electrical cable lengths over those in the sun tower design, the weight of these cables, along with the power management equipment, still forms a significant fraction of the total satellite mass. With this in mind, another concept was proposed that would substantially reduce power management and distribution mass. This concept, called the Integrated Symmetrical Concentrator, or ISC for short, would redirect the sun's energy by reflection, rather than first converting it to electricity and then distributing it over long cable lines. All of the concepts I've talked about have one thing in common. They are all too large to be brought to orbit and deployed in a single launch. For this reason, the systems integration team is currently looking at small, laser-based systems that can be launched and deployed as independent spacecraft without further assembly. These modular spacecraft would become part of larger constellations operating in or near geo-orbits. Such units could presumably start delivering power as soon as they are in place, and the delivered power could be increased as each new satellite joins the constellation. One of the most important systems integration functions performed for the SSP program is to develop computer models of these proposed satellite concepts. These models include key performance and cost characteristics of the many different technologies used in the satellite configuration. This information is provided by technologists from NASA, industry, and academia that make up the Space Solar Power Study Team. By having such models available, our systems integration analysts are able to compare the potential performance of the various satellite concepts and the benefits of using one technology over another, and pass this information back to the system designers and technologists. Through this iterative process, the whole project team ultimately becomes involved in producing the best possible design and technology approach for each concept. We're not there yet, but as we continue to come up with new and better concepts, as well as more accurate ways to model them, we feel that it's just a matter of time before we arrive at an SSP system design that we can confidently put forth as an economically viable alternative or supplement to more conventional and less environmentally friendly energy sources.
A variety of technologies are being developed to meet the challenges of delivering power from space. They include inflatable structures, innovative thermal management, robotic assembly, advanced PMAD and solar power generation, transmitter technologies, and solar electric propulsion. Near-term technology flight demonstrations will demonstrate their performance in space and advance their readiness to deliver power. A technology demonstrator at the 100 kilowatt level will provide a power-rich bus for a variety of experiments. Mission scenarios could include power beaming to a co-orbiting receiver satellite like Spartan, beam pattern calibration on the Earth's surface, solar electric propulsion for orbit transfer, or science missions such as a comet rendezvous. One proposed scenario utilizes the International Space Station as well as the new Advanced Technology Demonstrator. A low-power laser installed on the ISS Japanese experiment module back porch will demonstrate wireless power transmission to a tuned PV array on the technology demonstrator. The demonstrator co-orbits in front of the ISS at a distance of 10 to 20 kilometers. Both the laser on the ISS and the demonstrator itself are delivered to orbit by the space shuttle. After the ISS power transmission demonstration, the laser is removed from the GEM back porch and is returned to Earth on a later shuttle flight. Installation and removal from the external ISS site is done by the Japanese robot ARM and does not require EVA by astronauts. After the power beaming experiment, the demonstrator satellite uses its own solar arrays to provide 100 kilowatts of power to solar electric thrusters. The demonstrator will spiral out and away from the ISS orbit. Solar array options include the NTEC stretched lens arrays. With 100 kilowatts of power, the technology demonstrator provides a platform for other technology experiments. This could include alternative wireless power transmission technologies, solar concentrators, experimental PV systems, robotic assembly, innovative energy storage systems, or propellant production technologies.
Solar cells, much like those on a handheld calculator, would likely be used to generate the power on an SSP satellite by converting sunlight to electricity. However, power generation in space for an SSP system poses multiple challenges. First, an extraordinarily large area of solar arrays will be required for large-scale power generation. In addition, to hold down SSP system weight, solar array voltages much higher than any that have ever flown before may be needed. NASA and its partners are developing several different innovative technologies to meet this challenge. This is a key strategy. By pursuing several competing technologies in critical areas such as power generation, we dramatically increase our overall probability of success. Some of the technologies that you're about to see have the added advantage that they might be combined with one another, boosting power levels still further.
One path NASA is taking in its mission to develop efficient solar cells for space solar power is to create thin-film solar cells. Thinner and lighter than traditional silicon solar cells, thin-film solar cells require less material, as well as a lower-grade material. Therefore, thin-film cells are less expensive to produce. However, these cells have a complex structure, and high-quality cells are difficult to manufacture. NASA, in collaboration with the Ohio Aerospace Institute and Cleveland State University, has created a series of single-source precursor molecules. A single-source precursor molecule is a single molecule that contains all of the individual elements that are deposited on the final solar cell material. In this case, copper, indium, and sulfur or selenium are present in each single-source precursor molecule. The molecule is then grown onto the final, lightweight, space-qualified material. This simplifies the manufacturing process.
We've successfully produced a family of new compounds that can serve as single molecule precursors to a series of thin film solar cell materials. The deposition processes that we've developed using these molecules can be done at lower temperatures to enable the use of lightweight, space-qualified substrate materials such as Kapton. Also, other workers have shown that these thin film absorbent materials can withstand the rigors of the space environment.
To simplify the process further, NASA also developed a unique chemical process known as low-temperature chemical vapor deposition. In this process, single-source precursor molecules are sprayed as a fine mist into a chamber containing a lightweight, space-qualified material. Once in contact with the material, the molecules in the mist decompose at low temperatures, in fact, several hundred degrees Celsius lower than conventional processing. Once the molecules decompose, the molecules and the material become an absorber layer, or a layer of material that absorbs sunlight and converts that light into electricity. The absorber layers are then turned into thin-film solar cells.
What we've done is we've taken a chemically based approach. This enables molecular level or atomic level mixing of the elements. Because of this, we can do our deposition processes at much lower temperature. In fact, several hundred degrees lower in temperature. This enables us to do much lighter, use much lighter low-cost substrates, and consequently it's a much lower cost process.
To make thin-film solar cells truly practical for space solar power, NASA must continue to fine-tune its process for creating thin-film cells.
Well, the next step is to make more efficient cells. We also need to scale up our process so that we can deposit our solar cell materials on much larger substrate areas. Of course, space solar power requires extremely large areas, and we need to make a more manufacturable process to enable the use of larger equipment using a process that is much more reproducible.
Thin-film solar cells offer tremendous promise for space solar power by creating more efficient, lightweight, and cost-effective solar cells. However, this research can also benefit us in other ways.
There are many power materials that can be made using our process. Batteries, capacitors, fuel cells, and integrated electronics can all be produced using a chemically based process. Our chemically based process will allow us to do the depositions at lower temperatures using lower cost substrates and give us lighter electronics. And all of these benefits will improve our everyday lives.
Space solar power will require lightweight, high-efficiency, low-cost solar cells for power generation. Conventional solar cells have the potential to be 12 to 30% efficient in converting light to electricity, depending on the type of cell. However, when the new technology of utilizing quantum dots is incorporated into a solar cell structure, the cell's potential for converting light can increase dramatically.
Quantum dots are an extra layer of material within the solar cell structure that absorb the sunlight. They have the potential to double, possibly triple, solar cell efficiencies in converting sunlight to electricity.
First discovered in the early 1980s, quantum dots are basically a blob or group of atoms, and they are extremely small. In this image, a group of quantum dots are magnified to 4,000 times their original size. Without magnification, the dots measure 250 nanometers across. At 250 nanometers, approximately 20,000 of these dots could fit on Lincoln's face, on the front of a penny. Different sized dots absorb different types of light from the sun. While smaller dots absorb more blue light, larger dots absorb more red light. By controlling the manufacturing process, NASA can create quality dots that are the correct size. As a result, quantum dots have the potential to provide lightweight, low-cost, high-efficiency solar cells that are better adapted for the launch environment and have the ability to withstand radiation from the sun. Creating quality quantum dots that are the correct size proves to be a challenging task. NASA recently developed several different quantum dots for research, funded by the Space Solar Power Program.
We had to overcome quite a few obstacles to create the quantum dots. Our first problem was contaminants in the chemicals, which we had to then purify in order to synthesize the dots properly. Also, the size of the quantum dots is critical. Therefore, we needed to be able to create them in the appropriate size and isolate them so that we could eventually use them within a solar cell structure.
The next step for NASA is to create the solar cell structure in which the quantum dot can be tested.
We're at an exciting point in our research. We plan to develop a device structure in collaboration with the amorphous silicon group at Penn State University. We will build the actual quantum dot solar cell structure and test its efficiency. This will give us a comparison against the theoretical efficiencies of the quantum dot solar cell.
Solar array technology has made tremendous advances from the 10% efficient single crystal silicon solar cell to the 27% triple junction cell. However, many future NASA missions require power systems that must perform in harsh environments and at increased power densities. The Rainbow Photovoltaic Array concept offers the combination of high solar energy concentration and high efficiency power output. An experimental design of the rainbow array concentrates incident solar radiation through a parabolic Fresnel-like prism array that spectrally splits the light and directs it onto an array of different band-gap solar cells that match the energy of the incident light. The actual concentrator consists of a lightweight thin film, rigid array of prisms with solar cells selected to match the energy of the incident spectral bands. Band-gap matched solar cells were tested under the rainbow produced by the prism array as a demonstration of the potential for high power output. The rainbow concentrator uses prisms oriented on a cylindrical parabolic curve to spectrally split the incoming light and focus the resultant spectral bands on an image plane that supports the solar cell arrays. Modeling is used to determine the ray trace and focal point of the spectrum. A determination of the optimal prism type will maximize the power produced. Various prototypes of the rainbow concept were examined, leading to the present successful Prism Concentrator solar array design. The efficiency of the system is expected to reach 40%. The rainbow array can be constructed in a modular form and expanded to handle the needs of a wide variety of space and planetary high-power needs. Each module, consisting of a prism concentrator and an array of solar cells, can be added to meet the future power requirements of a space solar power system.
Our sun can be used to provide energy for a wide variety of space thermal applications, such as electrical power generation, thermal propulsion, or high-temperature furnaces. NASA is developing advanced concentrator technologies to concentrate and direct the sun's energy for these applications. One of these technologies is the refractive secondary concentrator. This concentrator collects light from a larger thin-film inflatable primary concentrator and focuses that energy into a high-temperature receiver.
The refractive secondary concentrator can be used in any system that requires the conversion of solar energy into heat. Our simulated space environment tests have successfully demonstrated that we can reach temperatures in excess of 2150 degrees Fahrenheit. The tests also successfully show that we can capture about 87% of the light that enters the refractive secondary. If we add an anti-reflective coating, we predict we can actually improve this efficiency to about 93%. This is important because the more efficient the system is, the smaller the concentration system needs to be. This translates into a system that's significantly lower in mass and is more cost-effective.
Made out of sapphire fashioned into a cone with a faceted extractor tip, the refractive secondary concentrator accepts a converging beam from a matched primary concentrator. Sunlight is refracted at the front surface of the cone, then reflected internally at the cone's sides and inside the extractor rod, which is inserted into a receiver. The faceted surfaces along the extractor tip broadly distribute the escaping light into the receiver, providing efficient, uniform heating. Many related components are used with the thin-film inflatable primary concentrator and refractive secondary concentrator system, such as a pointing and fine focus control system, thin-film rigidized support structures, and a high-temperature receiver. Together, these technologies have the potential to provide a lightweight, high-efficiency system that converts solar energy into heat.
Our plan is to bring all these technologies together and test them in a space simulation facility. This way we can see how these different components will work as an integrated unit in space. Testing in a space simulation facility like NASA Glenn's Tank 6 is really the next best thing to performing an actual spaceflight experiment.
Beyond space solar power, this technology has the ability to provide cost-effective solutions for the military and the communications industry.
In addition to power generation, this concentrator technology can also be used for thermal propulsion. We can use it for orbital transfer or for retrieving stranded satellites and moving them back into the proper orbit, much like a tugboat. Also, once the vehicle arrives at its destination, we can then use the same system to provide power and communications. Therefore, this system offers tremendous potential for multiple applications.
Many efforts have been made to integrate elements such as batteries and other energy harvesting devices with solar cells to enhance energy conversion efficiency and storage capacity. The power tile introduces several new technologies, including ultra-high efficiency solar cells, thin film thermoelectric devices, and inorganic solid-state lithium batteries. The conception of novel, extremely robust solid-state electrolytes has allowed for the creation of a new type of battery that is based on many thin film layers stacked on top of each other. These batteries exhibit excellent lifetime and environmental performance characteristics. Current testing showed that they could survive and function for 10 or more years in a variety of space environments. Thin film thermoelectrics create electrical current anywhere a significant difference in temperature is found. The greater the temperature contrast, the more energy can be derived. While larger thermoelectric devices have been fabricated and studied for years, the ability to make thin film mini-junction devices is just developing. A fully micro-fabricated thermoelectric device is shown on the left, and an image of thermoelectric elements made using nanowire template technology is on the right. Using these nano-dimensional elements, new technologies allow for heat to electrical energy conversion to be performed by an extremely lightweight and compact device. The traditional solar array uses many layers to support and protect the solar cell. Only about 10% of the volume of a typical solar array structure is actually devoted to energy harvesting. The idea driving the power tile is to replace as much of the passive structural components with active elements that aid in energy harvesting, storage, and control. The power tile is assembled by starting with a highly efficient photovoltaic cell that uses either the rainbow technology under development by NASA JPL or the more traditional multi-junction construction. A thin film thermoelectric device is then heterogeneously integrated on the backside of the solar cell. This device may be either micro or nano fabricated. For energy storage in times of eclipse, or to provide extra power during high drain duty cycles, a multi-layer solid-state battery is packaged onto the cold side of the thermoelectric device. Custom-designed ultra-compact integrated charge electronics are used for power management on each of the power tile modules. Finally, thermal management structures are used to help create the greatest temperature differential possible across the thermoelectric device. When sun is incident on the powered tile, the solar cell heats up to approximately 90 degrees centigrade in low Earth orbit. The thermal venting keeps the cold side of the tile at a lower temperature, less than 50 degrees centigrade, thereby providing the thermoelectric device with a sufficient temperature gradient. The charge electronics constantly provide power to the main bus, regardless of whether it must draw from the battery or the active elements. During times of sunlight exposure, the power tile maintains the battery at a fully charged state. Preliminary testing on the power tile devices shows that the thermoelectric element will likely be able to harvest a significant amount of power, thereby increasing the overall device efficiency by at least 5%. Current estimates show that the use of a fully functional power tile system could as much as double the continuous power-mass ratio as provided by current state-of-the-art solar cell array and battery systems.
Solar arrays turn light energy from the sun into electricity. In SSP, this electrical power is beamed via microwaves down to the Earth, where it is converted back into electricity. SSP's very high transmission rates require the building and testing of new solar arrays, which can operate above 300 volts and possibly 1,000 volts.
Solar arrays turn the energy and light from the sun into electricity. In space solar power, this electrical power is then beamed back to Earth and converted back into electricity again. In order to efficiently transmit the large amounts of power space solar power requires, very high transmission voltages are required. Tremendous weight savings result from generating this power at the voltage at which it will be transmitted. This is where high voltage space solar arrays will be essential. If high voltages can be achieved, these arrays can also be used to directly power electric propulsion engines, such as Hall thrusters and ion engines. We test the solar arrays at high voltage in a space vacuum plasma chamber, which simulates the low pressure and ionized gas found in space.
Analysis of orbital telemetry data from space satellites led to the discovery that power failures could occur at voltages as low as 80 volts. Tests have shown that this type of failure was due to arcing, or spark discharges, into the thin ionized gas of space. Arcing through plasma can burn up sections of a solar array and cause permanent short circuit. Yet SSP will require high-efficiency performance at voltages perhaps 10 times as great. Solar arrays that do not arc at voltages up to 1,000 volts have been and are being designed and tested in a simulated space environment. Work continues in order to establish new guidelines for engineers to build and manufacture high-voltage solar arrays for space. Our civilization depends on technology. Understanding how to make our technology work properly in space can benefit us all. Learning how to manage the abundant solar power available in space is key, not only to surviving and thriving in space, but also to using the space environment to improve life back here on Earth.
High-voltage solar arrays will be useful also whenever electric propulsion is needed in space. Future missions to the planets or Earth satellites that can change their orbits will depend on this technology.
In any electrical system, power must be moved from where it is generated to where it is needed. It is entirely possible that affordable SSP will require power to be distributed on board the platform at electrical loads in the thousands of volts, many times greater than today's satellites. Since this kind of system has never been flown, a great deal of research and technology development still needs to be done in the area of power management and distribution. However, we are confident that given adequate resources, the NASA-led team can develop efficient and affordable high-voltage power management and distribution systems for future SSP platforms. This next video segment will show two array regulators. One has the potential to be used with a microwave-based power transmission system. The other regulator would be used with a laser-based power transmission system. Both are key technology options for space solar power.
There are many significant engineering challenges in collecting large amounts of electrical energy from the sun, converting that energy with solar arrays into an acceptable form for transmitters, and then delivering that energy from the transmitters to Earth. For example, wires and electrical equipment with enough capacity to provide power to a small city are massive. However, because this system would operate in space, every component must be as small and lightweight as possible to enable launching at low cost. Meeting both of these requirements is very difficult. One solution is to develop high-power electrical components that can operate efficiently at high temperatures. If successful, this technology not only has the potential to significantly reduce the size of the wire conductors, but also reduce the size of the large thermal control system by a factor of 4. A NASA-led team has taken a revolutionary step by designing and constructing a preliminary version of a critical electrical unit to be used within the SSP system. The result is a solar array regulator with the potential to take advantage of the new high-power, high-temperature electrical components. In addition, with some small changes, this regulator could be reconfigured into two types of regulators. One regulator has the potential to transmit electrical energy using a microwave-based power transmission system, while the other regulator has the potential to transmit electrical energy using a laser-based power transmission system.
In the microwave scenario, our regulator would boost the array voltage tens of thousands of volts for efficient distribution over the long distances between the array and the transmitter. Also, with further research, this regulator could possibly be incorporated into relatively low-mass systems that would be acceptable for use in space.
The SSP microwave-based power transmission system would involve one large spacecraft that could capture radiated energy from the sun and reflect it onto solar array panels. The solar array panels would convert the radiated energy into electrical energy and transmit it via wires to the array regulator. From here, the regulator would boost the voltage to thousands of volts and deliver the power via wires to the microwave transmitter. The high-voltage electrical power would then be converted into microwave radiation and directed to a receiver located on Earth. In an effort to streamline the SSP system further, the NASA-led team modified their initial design and developed a regulator concept that could also operate using laser-based power transmission.
For the laser option, we used our regulator in a very clever way. Because the array voltage is very close to the voltage required by the laser source, we decided to process only 1/3 of the power through the array regulator and bypass the other 2/3 straight to the laser source. The end result is a regulator with very low mass and efficiencies of 98%.
A laser-based power transmission system would require multiple, smaller spacecraft to collect energy from the sun. As with microwave power transmission, the solar array panels would convert the sun's radiated energy into electrical energy. The electrical energy would then be transmitted to the array regulator via light beams instead of wires. This reduces the system's mass significantly. The array regulator would then increase the voltage to hundreds of volts instead of thousands of volts and control the output within a small variance to enable higher efficiency levels. From here, the power could be channeled to either a single laser or a set of laser diodes. The diodes would create many small laser beams. These beams would then be combined optically into one large beam. Studies are ongoing to determine the best method for providing laser power. The use of high-power, high-temperature electronics offers potential benefits for both microwave and laser-based power transmission systems by reducing the mass of the wires and the size of the thermal radiator. While the NASA-led team has made significant strides in understanding the type of power management and distribution system required for space solar power, more research is needed to determine whether the array regulator will successfully meet the efficiency levels and low mass requirements necessary for SSP, while at the same time withstanding the rigors of space.
So far, we've completed a concept to determine the best type of system that would address the unique concerns of space solar power. Next, we need to build prototypes and test them in a simulated space environment. Only then will we understand how well our regulators perform.
While the array regulator offers the potential to regulate extremely large loads of power for SSP, it also provides benefits for future NASA missions.
These two similar but different regulators are examples of our design philosophy to evolve a catalog of parts. With a few minor modifications, these catalog parts could be used to accomplish 80% of the missions that NASA ever launches. That's a tremendous benefit because it reduces the cost and the risks associated with future NASA missions, and that benefits everyone.
Transporting anything to space and in space is an expensive proposition. Therefore, NASA is developing extremely lightweight, collapsible structures that could be used to build many of the parts of future SSP platforms. Moreover, in many ways, space is an extremely harsh environment. Therefore, the materials from which the framework of an SSP platform is built must be able to withstand its rigors, and to do so through decades of operations. Here you'll see some of the inflatable, space-qualified structural concepts that NASA has developed for use in future SSP systems.
NASA is developing advanced structures and materials technology for space solar power systems. Large space solar power satellites will be constructed from thousands of pieces launched into orbit. These pieces will be joined together by astronauts and robots to form the primary structure of the satellite. The primary structure supports the giant reflectors at each end of the satellite that collect and focus sunlight, the solar arrays that generate electricity, and the microwave transmitting antenna that beams power down to Earth. At NASA, researchers are developing new concepts for lightweight structural elements such as inflatable trusses. Inflatable structures can be folded up into much smaller packages than other types of deployable structures. Many of these small packages can fit on a single rocket. This reduces the number of rocket launches required to construct the solar power satellite and lower the cost. After reaching orbit, the structural elements are inflated like a balloon to form large truss sections. The truss sections are then rigidized so that it is not necessary to maintain pressure in the structure to hold its shape. During rigidization, the composite material in the structure becomes stiff. Some types of inflatable structures are rigidized by heat. Other types are rigidized by cooling or by ultraviolet radiation from the sun. Once the truss sections have been rigidized, they are assembled to make larger beams and girders, which are used to construct the backbone of the solar power satellite. The backbone of a large power satellite may be several kilometers long. It holds the solar reflectors in the proper orientation so that they focus sunlight onto the solar arrays. Researchers at NASA are investigating structures, trying to improve our understanding of how these structures perform and how they can be scaled up to larger sizes.
This is an inflatable, rigidizable tube. It's already been inflated and rigidized, very much like it would be on orbit. But before it gets to that state, it starts out as a packaged, rolled-up piece of composite fabric. It's taken to orbit, and then it's inflated very much like this party favor. And then it's rigidized through various methods on orbit. It can also be folded very much like an accordion, where it folds out, is inflated, and also rigidized.
Many tests are conducted in the laboratory to measure the strength and stiffness of inflatable booms and trusses. In these tests, a steadily increasing compressive load is applied to the structure until it fails. The test data is used to validate mathematical models, which will be used for the design and analysis of structures for space solar power systems.
This is an inflatable, rigidizable truss structure. It's composed of these inflatable, rigidizable tubes. The advantage of this structure is that it can be compressed into a very small packaging space. When it's launched to orbit, it can then expand into this large truss structure. It's very stiff after it's been rigidized. And then it can take quite a bit of load. We've actually tested this structure, and it handled 550 pounds of load, which is quite a bit considering it only weighs approximately 10 pounds and is very lightweight. So it actually handled 50 times its weight in load.
In addition to inflatable truss sections for the satellite backbone, lightweight, deployable structures are needed to support the solar arrays. An isogrid boom is an inflatable boom that is fabricated by wrapping carbon fibers in a spiral pattern around a cylinder. The fibers are bonded together where they intersect to form a sparse network with open spaces between the fibers. Because it uses less material, an isogrid boom is lighter than a simple tube, but it has almost the same strength since the fibers are placed only where they are needed to carry the load. Isogrid booms are developed for lightweight solar arrays.
The isogrid column is a very lightweight structural concept. In particular, this 3-meter column can hold up to 100 pounds of actual compressive load and yet weighs only 6 ounces. The column is made of thermoplastic epoxy and carbon graphite fibers. Thermoplastic materials become pliable when heated above their glass transition temperatures. So this column can be packaged simply by heating it and rolling it up. To demonstrate deployment, a 3-meter column was deployed in a thermal vacuum chamber. The temperature inside the chamber was very cold at 135 degrees Celsius below zero. The cold temperature and vacuum inside the chamber simulated the environment of space where the column will be deployed when it becomes operational. A column was coiled inside the gold box, which was actually an insulated oven designed to warm the bundled structure. When the column's core reached a very hot temperature of 80 degrees Celsius inside the oven, a minuscule amount of nitrogen gas was released into the column. In a vacuum, the gas expands rapidly to fill a large volume with a force great enough to fully extend the column in just a few seconds.
Concepts for inflatable, deployable space structures have been under development and evaluation for almost 50 years, as exemplified by the Echo balloon, built, launched, and deployed in the early 60s. The approach offers low-cost hardware, exceptional packaging efficiency, deployment reliability, and very low mass. These features remain attractive in potential applications such as solar sails, large antennas, and structural elements in space solar power concepts. Recent technology developments introduce materials and rigidization techniques to form many components, including trusses, joints, reflectors, and special-purpose components. An example is shown of Inflatable Antenna Experiment's 14-inch diameter, 95-foot-long beam in its pre-deployment package of 13 inches. The Inflatable Antenna Experiment, or IAE, is the most remarkable demonstration to date of inflatable, rigidizable technology. More than a demonstration of antenna technology, it is a demonstration of applications. Inflatable structures offer the same benefits to space solar power and are especially attractive given the kilometers-long size required for SSP solar collectors, concentrators, radiators, and other components and frameworks. Crucial to the next generation of inflatable devices is the development of truss and joint configurations capable of sustaining the shape and function of supported components. A full-scale truss section pictured here provided initial determinations of material and mechanical properties of very large-sized inflatable space structures. For SSP, a rigidizable truss was constructed consisting of 3 tubes or longerons, 1 1/2 inches in diameter, 40 inches long. Each tube, made of 3-ply carbon fiber laminates, was folded and stowed with the diagonals attached. This element or bay was then inflated and rigidized with an embedded thermoset plastic. The test results showed a high degree of straightness, uniform circular cross-sections, and highly compatible tube and joint dimensional repeatability. These successes demonstrate that current technology enables large structures. Further effort will increase packaging efficiency, extend materials life, standardize manufacturing processes, and integrate deployment and control features, permitting an entire class of inflatable structures for a broad range of space applications, including those of space solar power.
Because inflatable and membrane structures are very large and lightweight, they will also be very flexible. This means that the structures will tend to vibrate when disturbed by small external forces. These vibrations can prevent the solar power satellite from accurately tracking the sun, which is critical for collecting solar energy efficiently. In addition, the surface of the microwave transmitting antenna must be kept very flat so that the beam is not distorted. Researchers are working on concepts for suppressing unwanted structural vibrations and for controlling the flatness of large apertures like the antenna. These new control methods are demonstrated on a smart structures test bed called a hexapod. The hexapod consists of a 3-meter diameter reflective membrane suspended in an inflatable frame. Piezoelectric actuators are embedded in the inflatable frame to dampen out its flexible dynamics. Other actuators are attached to the reflective membrane to adjust its tension and control its flatness.
As part of the space solar power activity that we've been working on, there are 2 problems that we are concentrating on. One is vibration control of membrane and vibration control of inflatable rigidizable structures like the one we have here. This past year, we spent quite a bit of time looking at actuators that would allow us to do vibration control of membrane structures. And this actuator I have here is the first prototype of such a system. It'll be mounted on this structure like this, and it allows you to do in-plane tension control and it allows you to do out-of-plane vibration control. And our hope is to fit this particular structure with actuators so that we can demonstrate our ability to control a membrane like this. The second problem we are working on is the actual vibration control of the overall system. And for that, we've chosen the NASA-developed microfiber composite actuator, which is one. Here is one. It's a very paper-like actuator that was bonded on the structure at key locations, and this would allow us to control the vibration of the overall configuration.
It is likely that SSP structures will be built in factories here on Earth and then transported into space. To accomplish this ambitious task, NASA and industry are developing reusable launch vehicles, known as RLVs, that could carry large payloads into space cheaply and reliably. Once launched into a low Earth orbit by an RLV, the many elements of an SSP system must be moved from there on up into a geostationary Earth orbit. Achieving this affordably will require advances well beyond today's propulsion systems. Highly efficient electric propulsion, also being developed by NASA and its team, would do the job. Because geostationary Earth orbit, also known as GEO, is about 22,000 miles higher than the orbit of the International Space Station, moving SSP system elements to their final destination poses a significant challenge. This next video segment, you'll see, demonstrates NASA's reusable launch vehicle technology and how it works. A second video segment will then illustrate the electric propulsion technologies that could be used to transport the elements of an SSP system in space.
The delivery needs of large-scale space solar power will help create the demand for tomorrow's space transportation. Modular and robust packaging of space solar power elements will allow space cargo to be handled in bulk. Highly advanced space transportation vehicles launched from high-throughput spaceports will allow very low-cost delivery of the materials and components needed to provide energy from space. Advanced methods, such as the maglev ground launch assist concept, may emerge and transform today's launch complexes into multimodal gateways to the space frontier.
To effectively collect energy from the Sun, the Space Solar Power Platform must be placed into the geosynchronous orbit, or GEO. However, GEO is located 22,300 miles above the Earth's surface. This is approximately 22,000 miles beyond the International Space Station. Therefore, a tremendous amount of propulsion is required for this task. To transport the power-generating station to GEO, heavy lift launch vehicles would deliver the payload to LEO, or low Earth orbit, approximately 200 to 300 miles above the Earth's surface. From there, the spacecraft would deploy itself, and the propulsion systems would then transport it to its operating position. NASA has developed two electrical propulsion systems to accomplish this task: the Hall thruster and the high-powered MPD, or Magnetoplasma Dynamic Thruster.
For space solar power, we're looking for a very fuel-efficient propulsion system. Compared to chemical propulsion systems, which basically use a chemical reaction to provide the energy and therefore the thrust of the engine, we are looking to use electrical power to provide the energy for the thrust. There's two ways to do that we're choosing for the space solar power system. One is the Hall thruster, which basically uses electrical energy to provide a high-energy electrical field which accelerates a gas to very high speeds, 10 times the speed of a chemical rocket. For the other choice we're looking at, to have another choice, is the MPD thruster. In this case, we take a magnetic field, a very high energy magnetic field, and accelerate a gas in that way. So we basically have two ways to take electrical energy and turn it into a very high fuel efficient thrust.
While the Hall thruster is very fuel efficient at kilowatt power levels, the MPD thruster provides better thrust density and performance at megawatt power levels. High-powered cathodes used to carry electric current are integral components of both the Hall and MPD thruster. Developed by NASA, the Hall thruster cathode works much like a spark plug in a car, initiating a charge that will help accelerate the thruster. However, NASA's propulsion technologies have applications that go well beyond space solar power.
The really exciting thing is this technology will be good not only for space solar power, but for other uses. For example, it'll allow us to put more TV satellites up into orbit. The best thing it could probably do is help people explore the universe, send people to Mars, even send people out to Jupiter or other places. This propulsion system is so fuel efficient that it allows us to do that in a very affordable way.
The on-orbit assembly and maintenance of space solar power satellites is a challenge to future space transportation systems. The number and frequency of space solar power satellite launches will provide the economies of scale that will help drive down the cost of space transportation.
Once in space, individual structures and equipment that will make up the space solar power system must be assembled and operated and then repaired. Because these systems would be located in a high orbit, roughly 22,000 miles beyond the International Space Station, astronaut house calls, such as those made to repair and upgrade the Hubble Space Telescope, will be difficult and extremely rare. To meet this challenge, NASA and its team have been developing several highly innovative robotic concepts that could be used for the purpose of assembly, maintenance, and servicing of future space solar power systems. Once launched, these robots would live permanently on the SSP platform. In the following video segments, you'll see some of the clever robot concepts that might someday be launched into space for assembling and maintaining large SSP platforms.
Due to the proposed size and complexity of the space solar-powered satellites, it was previously estimated that it would take hundreds of human astronauts a tremendous amount of time to construct and move the required hardware into geosynchronous orbit. Add to this the risks that the spacewalking astronauts would have to endure, things like ionizing solar flares, other galactic radiation, and the constant barrage of micrometeoroids, and it seemed almost impossible to make the dream of space solar-powered satellites come true. But NASA is well known for turning the impossible into the possible, and the solutions to those problems are closer than most people realize.
We're now reassessing whether or not with today's robotic technology we could fulfill some of those good ideas in a new way. Instead of having to only use crew, we have these new options that we can mix into the assembly team.
New generations of robots, such as Johnson Space Center's Robo-Naut, with its ability to handle extremely intricate and precise tasks, pave the way to the future of robotics.
Because each new creation teaches us more about those fundamental technologies, this pace of evolution continues to accelerate. We can create new and unusual robots for new and unusual tasks much more quickly today than we could even 5 years ago.
Entire new species of robots are being developed, each designed according to its specialized job. NASA intends to continue developing technology that will augment human capabilities to deploy, assemble, maintain, service, and operate large systems such as the space solar-powered satellite. These innovations will not only minimize the human risks of space construction, but will also diminish costs by reducing the number of launches needed to boost the payloads into geosynchronous orbit.
These robots can be working 24 hours a day. They can stay out permanently. They don't have to come back into a spacecraft that's pressurized. And we're not risking their lives. If they're injured, well, we'll feel sad, but we can build new ones. They can keep working, and we will not be risking their lives. The crew can operate them safely from back in their spacecraft or even from on Earth.
Robots of the future will not only be used to build large surface science platforms in space, but also to conduct research and even set up and maintain outposts on distant planets such as Mars or beyond. Whether they are working as assistants to spacewalking astronauts or remotely with human supervision, it's clear that advances in robot technology will allow humans to achieve more in the far reaches of space than ever before.
Although space solar power constellations will be of immense scale, assembly, inspection, and maintenance activities will require intricate operations in restricted and confined spaces, in addition to the manipulation of large components. For these operations, a class of multi-limbed, agile, dexterous robots is envisioned. A first generation of the Limbed Excursion Mechanical Utility Rover, or L.E.M.U.R, is equipped with a variety of sensors and interchangeable tools to perform a multiplicity of tasks. Forward-mounted stereo cameras provide visual navigation information and vision-based control of limb tools. In addition, pole-mounted optics enable close-up inspection or direct visual servo control of the gripper. A combination of these capabilities facilitates complex operations, such as the removal of a damaged or worn part. Using visual feedback of fiducial markers or cues on the end effector and task board allows precise localization of the arm-mounted driver relative to the fastener head. As task complexity and scale increase, behavior-based software architectures will allow the coordination and cooperation of multiple service robots to achieve required goals of autonomous operation, maintenance, self-support, long life, and high reliability.
It is likely that power from SSP systems in space would be transmitted to Earth using a low-intensity microwave beam. Past research confirms that no negative effects are expected and that the low-intensity microwave beam used for sending power down from space would be much safer than many other forms of energy in use today. However, even though most households already use microwave technology, its use for long-distance power transmission will most probably raise concerns about the possible effects of microwave energy on living things. In this next segment, you'll see how NASA is investigating the potential effects of microwaves on plant life. It is believed that still more research will be needed to assure the future safety of microwave power beaming.
Not much is known about how plants, animals, and humans will respond to continuous microwave exposure. Our experiment will show how an important plant species will respond to continuous exposure to microwaves. Our hypothesis is that plants exposed to microwaves will be no different from those plants that are not exposed to microwaves. The microwaves for this experiment are generated by a device something like that in your cell phone. This microwave generation device is called a Voltage Control Crystal Oscillator, or VCO. Microwaves at 2.45 GHz and at 1 to 10 milliwatts per square centimeter intensity are generated in the oscillator, pass through a short cable, and are broadcast over the growing plants by the antenna or emitter horn. The microwaves are then bounced off the adjustable reflector, thus exposing the test plants to the microwaves. Note that the plants growing behind the metal sheet or shield, the control plants, do not receive any microwave exposure. The experiment is designed so that the only variable to which the plants are subjected is microwave exposure. A plant representative of important agronomic species is alfalfa. The plants are grown in a potting mix in plastic pots. A measured amount of soil is placed in each pot. A measured amount of alfalfa seed is placed in each pot. And the soil is moistened. The light necessary for photosynthesis is supplied by an overhead rack of fluorescent tubes and several incandescent light bulbs. To test the hypothesis, precise measurements are taken of the control and experimental plants. Variables measured include gas exchange. Another variable measured is leaf chlorophyll concentration. Also measured are gross plant variables such as stem length, internodal distance, and overall vigor. These experiments are ongoing and will be expanded to include mixes of plants and growth of plants from seeds whose progenitors were exposed to the same level of microwave frequency and intensity. These studies will help determine whether plants can grow in an environment of sustained microwave illumination.
A number of other areas of research and technology are being advanced by NASA that could further enhance the capabilities and the cost-effectiveness of future space solar power systems. Next, you'll see some of these exciting areas in which other technologies are being researched that might someday help to meet tomorrow's energy needs.
Many concepts are being considered for the spacecraft platform that will integrate the solar panels, the transmitter elements, and all of the other components of a complete power station. Here is one concept, a conservative baseline, one that will probably never fly, but one that will permit us to develop the system-level requirements and allow us to estimate the maximum cost of a power station. Each of the 2 solar array panels is 10 square kilometers. Each row in the panel is individually driven to continuously face the sun. Failure of the drive mechanism in any one row will leave the power plant fully operational. The phased array transmitter is about 1 kilometer in diameter. The Terra spacecraft is shown for comparison. The transmitter antenna continuously beams 1.2 gigawatts of microwave power to the receiving antenna on the ground. The power station structural elements are the central transmitter toroid, the vertical strongbacks, and the individual horizontal row strongbacks. The power generated in the solar panels is sent on a 40 kilovolt bus to the central strongback through roll rings that each pass 5,000 amperes. Solar panels can be individually replaced. The arrays are kept flat by ion engine thrusters, which are first used to raise the power plant modules from low Earth orbit and then are used for station keeping and attitude control. The spacecraft replacement components and robots are housed in the garage and warehouse. The electronic boxes on the transmitter toroid are the power station's distributed control center. All communication between them and all other modules are via low-level RF links. The transmitter has many tens of thousands of individually controlled modules. These modules are plugged into a grid structure and can be individually replaced. The modules are individually pointed to the ground antenna. A guide beam from the ground antenna site is used to control the phasing and pointing of each module. Several small antennas around the edge of the module receive this beam.
Space Solar Power, Science, Research, and Development at JPL has produced innovative concepts, designs, materials, and laboratory demonstrations. One candidate architecture for SSP power generation and transmission is the HALO concept, which offers the potential of reducing the mass of a solar power system. This concept uses HALO orbital mechanics to position mirrors that direct sunlight to a central power converter and transmitter. Simulations of orbital configurations and force models have shown the viability of the HALO concept to maintain a constant power beam as a function of mirror angular rates and sun incidence angles. Materials development activities have resulted in lightweight carbon-carbon sails exhibiting superior strength at high temperatures. These materials offer low aerial mass and are amenable to various surface modifications or surface treatments. Hence, they may be structured for optimal thrust-to-power ratios under solar, thermal, infrared laser, or microwave irradiation. Carbon sails have been used to investigate the physics of laser-powered flight in vacuum environments. Other tests in a small vacuum chamber using microwave power demonstrated the rapid heating and acceleration achievable by these sails. Theoretical calculations predict accelerations up to 100 gravities with this technique. Various deployment and stability concepts have been demonstrated in the laboratory. These tests show the feasibility of generating torque produced by photon angular momentum for stability and deployment. Computer simulations suggest that polarized microwaves can be used to deploy large solar sails and other gossamer structures. By modifying the surface optical properties and the gas-surface interactions, carbon sails have been levitated in rarefied gas against gravity. By using thermomolecular forces and air-breathing sails, high-altitude platforms are possible. Furthermore, this technique may be possibly used to lift gossamer spacecraft through the atmosphere. These activities result not only in a greater understanding of beamed power, but also in the development of advanced concepts and demonstrations to enable beam-riding spacecraft. spacecraft capable of high acceleration and stability within a directed beam of light. The increasing complexity and sophistication in space exploration demand that space systems meet expanded flight performance requirements, recover from failure or degradation events, increase reliability, and reduce cost. Integrated vehicle health monitoring is the first step towards autonomous systems capable of self-diagnostics, prognostics, maintenance and repair, and ultimately adaptive spacecraft. MEMS technology provides a cost-effective way to achieve distributed sensing and health monitoring. Capitalizing upon SSP development of an inflatable truss, a multi-sensor package was conceived that would be mounted on the truss test article. In this manner, appropriate mechanical and performance parameters could be evaluated against a specific space design element. In a first-generation device, 4 types of MEMS sensors, temperature, pressure, strain gauges, and accelerometers, were chosen and mounted on a flexible laminate substrate. The sensor package was then mounted on a flexible tubing and tested for adhesion and sensor function. In this sensor package, deep reactive ion etching techniques are used to form low-profile sensors while achieving high aspect ratios necessary in pressure sensor diaphragms and accelerometer-proof masses. Fusion bonding generates high bond strength suitable in high-acceleration space environments. Circuitry is embedded in the flexible substrate ready to attach to the test element. To determine where and what type of physical sensing is important, probabilistic failure assessment, or PFA, is being used. Material and mechanical properties as well as environmental and operational parameters will be evaluated to determine critical aspects in SSP design and performance, and provide insight into diagnostic and prognostic protocols to achieve high reliability. Incorporation of actuators with embedded sensors result in an active system that can both sense and interact with the environment. Electroactive polymers, or EAP, are capacitive-based materials that show large actuation strain when a voltage bias is applied. Appropriately placed sensor actuators can correct deformities in inflatable components and adjust antenna or reflector surfaces in SSP structures, and have applications in a wide range of space endeavors.
One of the most exciting aspects of pursuing the development of SSP technologies is their expected importance in diverse near to mid-term applications. All of the spacecraft currently flying or planned, from communication satellites to the International Space Station, will benefit from advances in space solar power. The same will be true for many expected spin-offs of these technologies in Earthbound applications. Moreover, most of the ambitious missions and capabilities planned for the future in space will be realized only if we can achieve our SSP goals and objectives. Whether launching a space business park or establishing a human outpost beyond low Earth orbit, whether enabling large-scale space tourism or sending a human mission to Mars, all might benefit from affordable and abundant space solar power. This next segment illustrates briefly some of the many anticipated benefits that will result from the progress we have made and that we hope to make in the future in the area of space solar power.
Membrane structures are very thin sheets of film supported by deployable masts and booms. Large membrane structures will be used in space solar power satellites, for the solar arrays, and the solar collectors. Ultra-lightweight membrane structures are also needed for other NASA missions, such as solar sails and sunshades for large space telescopes. NASA researchers are developing concepts for packaging and deploying large membrane structures.
The research underway in this facility is to study the integration of the solar sail materials, the membrane sails, with the ultra-lightweight booms. The studies are trying to determine the best methods for packaging and deployment of membrane structures. Behind me you see a 2-quadrant model of a solar sail. This model deploys vertically, and as it does, it pulls the sails and stretches them taut. Part of the studies are trying to determine the loads the boom sees during deployments and the best methods for tensioning the sails to prevent wrinkling. These studies are being done with constant thickness scale models to validate the design tools we're using for future space missions.
The test bed consists of a 10-meter wide triangular membrane supported by an inflatable column. The test bed has been set up in one of NASA's vacuum chambers, which simulates the space environment. It's important to test membrane structures in a vacuum because the air surrounding the membrane can change its dynamics. The vibrations of the membranes will be measured with laser beams reflecting from its surface. This information will be used to predict the behavior of large membrane in space.
Under the Space Solar Power Science Program at laboratories at JPL, universities, and DoD facilities, a concentrated systematic development effort has been underway to use the basic concepts of SSP, beamed power, lightweight high-strength structures, and advanced solar cell technology to enable a new era of space exploration. Photons have different frequencies, and different frequencies have different advantages. Microwave photons are easy to make and can impart large amounts of angular momentum. Optical frequencies, such as produced in this high-energy Air Force facility, have the advantage that the aperture of the transmitter can be smaller, an important factor in the cost of any system. The first step in the program is to verify the basic physics of moving a sail with light. This step must be done in a large vacuum chamber to simulate the conditions of space. The simplest way of verifying the physics is to mount a sail on a pendulum. The sail moves as the laser fires, receiving momentum from the beam of light.
Yeah, the results of this test were quite exciting for us. We actually measured the deflection of the pendulum as a function of laser power. For the powers in the range of 8 kilowatts on up to about 14 or 15 kilowatts. What we measured were deflections up to about 12 degrees, and well, we demonstrated for the first time in history the measured forces of photon pressure on a real light sail material.
Now that forces have been measured with the pendulum, the next step is to fly a sail. The first flight of a laser-powered sail is guided by wires. The first flight of a laser-powered sail verifies the basic physics. At JPL, a large vacuum chamber has been set up for wire-guided flights at microwave frequencies. At microwave frequencies, the wavelength of the radiation is on the order of the size of the sail. Because of this, the distribution of heat of the sail must be understood to prevent any burnouts of the microtruss carbon fibers. It is the high temperature of these sails that enable high accelerations, theoretically up to 100 Gs, that make the beam-powered sail flights feasible in the foreseeable future.
The promise of this propulsion method can be put quite simply. With rockets, it takes about 10,000 years to get to the nearest star. With this new mode of propulsion, it would only take about 40 years.
A robotic mission to the Moon can mature space solar power technology and answer key scientific questions. For this mission, a lunar lander carries a robotic rover to land precisely on a mountaintop near the Moon's north or south pole. Upon landing, the rover is deployed to the Moon's surface. Based on our experience with the Apollo lunar roving vehicle, this rover can travel long distances using electrical power. The lander and rover deploy photovoltaic arrays to change light into the electrical power required for telemetry, laser beaming from the lander to operations of the rover. Subsystems are initially checked out on the lunar polar mountaintop in continuous sunlight. Then the rover uses laser light, beamed from the lander, to descend into lunar polar craters where the sun never shines.
Development of a novel actuator powered by radiant energy. Future exploration and development of space require new developments in actuator systems. The ideal actuator for space applications would be strong, lightweight, require minimal maintenance, and use readily available energy resources. A novel actuator with many of these features will be demonstrated here. This actuator is comprised of a shape memory alloy and an integrated energy collection mechanism. When combined, this system produces a highly energy-efficient actuator by initiating a phase change, and thus motion, in the material due to the addition of collected energy. Consider the proposed actuator system depicted here, consisting of a support cable with integrated shape memory alloy center. When properly controlled, this actuator is capable of changing length and producing significant tensile forces. In the space environment, solar radiant energy is a readily available power source that will be harnessed to drive the actuator. The actuator is completed with an energy collection mechanism to concentrate radiant energy into the SMA. For example, by using a thin film lens or parabolic trough. This concentrator controls the level of input energy or shields the SMA to allow actuator cooling. A prototype of the actuator was built to demonstrate proof of concept. The simple prototype is made of cylindrical concentrators located about a shape memory alloy wire. This wire is radially constrained to lie along the focal length of the concentrators. Temperature and position sensors along with drives for the concentrator complete the system, allowing actuator control. This video clip demonstrates alternately concentrating and shading light on the shape memory alloy. A key characteristic of this actuator system is that a small amount of energy expended in orienting the concentrators can result in large amounts of output actuator energy. SMA behavior is characterized using readily available models. For example, the phase fractional envelope plots shown. These plots demonstrate the ability of both the mathematical model and prototype to follow a prescribed displacement profile. Note that saturation of the actuator at high displacements is predicted in the mathematical model and observed in the physical model. Why should this proposed actuator be used when other actuators are available? It has substantially lower power requirements, it can significantly save mass, it can easily be implemented in a highly distributed actuator system. This novel actuator has been developed and tested and has demonstrated high efficiency, reduced weight, and maintenance costs for space applications.
Global warming, we now know, is of course due primarily to the release of carbon dioxide. This global warming is associated with about every electricity production method that we know. And the question is not which one will we choose, except perhaps nuclear or fusion power, but even they have certain drawbacks, as we all know. The only one that is most compatible with the environment and will not produce the global warming caused by burning fuel is the power we beam to Earth from the sun. In this slide, we graphically demonstrate that we have increased our population from a little bit around 2 billion people, that we now see us having 10 billion people on planet Earth. This increase in population appears to be nearly unsustainable if you look at the availability of energy and the conservation of the environment. In the next slide, we see the kind of challenge we face because now we are reaching the maximum availability of energy sources. We now expect that by the middle of this century, all of these energy resources will have been nearly exhausted, and we can no longer maintain the population on planet Earth to the degree that they will demand, and thus new energy sources which no longer rely on terrestrial energy sources will be required. And the best source that we have access to is solar energy. Because all the data and papers and presentations that we made here in the US and in various international congresses were of great interest to many other nations. And thus it's not surprising that the one nation which probably can use space solar power to the greatest advantage is Japan. And Japan used the kind of information that they already could get to start their own space solar power program. And this slide shows some of the early developments that they were doing in this area. The Japanese then performed probably the most single challenging experiment in this field. And that was to launch a satellite and another satellite. And one satellite would beam microwaves to the other satellite. And this slide shows the program as presented at an international space congress by some scientists from the Soviet Union, indicating that they also are working on space solar power and that they have thought through several of the important steps that will have to be taken in order to demonstrate at various times the kind of technologies which they hope to develop. The role of the United Nations in space solar power down the road will be essential, because all the nations will have to have inputs to the basic questions that they ask. Well, who controls it? And who benefits from it? And how can we be assured that somewhere somebody will not interrupt the essential power supply if we rely on space solar power? I am certain that with the goodwill of all the nations and with the help of the United Nations staff, we can arrive at the necessary legal framework to make this work for all people on Earth for as long as the sun will shine. Here you see the distribution of the microwaves as they are received at the antenna. At the highest level, they're about a quarter of the energy of sunlight. So we are dealing with a very diffuse energy source. At the edge of the antenna, we are close to the kind of international safety rules for microwave ovens. For example, each microwave oven is designed to be safe with the door closed so that you're not exposed at all to microwaves if you're at least 4 feet away from the oven. Similarly, this is a rule we have at this receiving antenna, so that unless you climb over the enclosure, you will not be exposed to microwaves any place beyond the perimeter of the antenna. There was one concern we had, and that is when we beam energy back to Earth, we have to re-enter certain portions of the atmosphere. And some of these portions have an effect on the electrical properties of the high atmosphere. Now, how do we make sure that we do not interfere with these upper atmospheric conditions? Well, the simplest is to use an antenna, an existing antenna on Earth. And that we did in the location at Arecibo, where is a mile diameter receiving antenna for various space experiments. And that way, we were able to demonstrate that the microwaves coming back to Earth will not interfere with the radio communications from other sources here on Earth, because we're not heating up some of the upper atmosphere layers which are crucial for this purpose. Nothing ever built arose to touch the skies unless some man dreamed that it should, some man believed that it could, and some man willed that it must. This quote by C.F. Kettering summarizes my feelings about space solar power.